Our purpose is to investigate 6 equilibrium systems to gain a deeper understanding of equilibrium and Le Châtelier's principle. If an equilibrium is subjected to a stress, the system will react in such a way as to reduce the stress.
According to Le Châtelier's principle, the increase of the concentration of a reactant will favor the forward reaction. In this instance, as more iodide ions are present, more of the other reactant, iodide, is needed to react with it. As a result of its increased reaction rate, iodide becomes more soluble. When the temperature of the endothermic reaction rate number increases, the forward reaction is favored. The concentration of the product, nitric oxide, increases in order to maintain equilibrium. When the pressure of the same reaction increases, volume decreases, which means that the side with fewer moles is favored. However, since there are 2 moles on each side, the concentrations do not change. First, measure 20 milliliters of potassium thiocyanate solution and pour it into the petri dish. Record the initial color. Now, add 3 drops of iron nitrate and swirl the solution. Record the color change. Add half a pea-sized amount of potassium thiocyanate crystal and wait 30 seconds. Record any change in color and swirl the solution. Repeat the same process with potassium nitrate. Next, add a quarter of a pea-sized amount of sodium phosphate crystal and wait 60 seconds. Swirl the solution and record the color change. Add 1 drop of iron nitrate solution and record the change in color. Finally, add a pea-sized amount of potassium thiocyanate crystal and wait 30 seconds. Record any color change and keep the final solution. The beginning solution was clear. After 3 drops of iron nitrate solution, it turned light orange. After the addition of potassium thiocyanate crystal, the solution changed to a dark red. When potassium nitrate was added, it stayed dark red. The addition of sodium phosphate turned the solution clear again. When iron nitrate was added a second time, it became an orange-reddish color. Finally, with the second addition of potassium thiocyanate, the solution turned to a pale red.
Start off by filling 2 beakers with tap water. 1 beaker will be heated to 65 to 70 degrees Celsius to be a hot water bath, while the other will be filled with ice to be an ice water bath. Next, label the 2 test tubes A and B. For each tube, add 10 milliliters of the complex ion solution from part A. Test tube A will be the control. Now place test tube B in the ice water bath for 3 to 5 minutes. Record the color in comparison to test tube A. Then, place test tube B in the hot water for 2 to 3 minutes. Record the color in comparison to test tube A. Lastly, wash the materials. Moving on to the results. Initially, the solution had light yellowish clouds towards the bottom of the test tube and was clear at the top. After being placed in the ice water bath, the bottom appeared to be a darker yellow and cloudier while the top remained clear. After the hot water bath, the bottom of the solution was a pale yellow and had wispy clouds throughout the test tube.
The chemical equation for the reversible reaction observed is 1 iron 3 ion and 1 thiocyanate ion, yielding an aqueous iron thiocyanate. The color of the solution changed to a dark red and back to clear when additional potassium thiocyanate was added, indicating a reversible reaction. When additional drops of iron 3 nitrate were added in one spot, the solution turned red in that area, proving the favoring of the forward reaction since more of a reactant was added. The color did not change when potassium nitrate was added because it does not affect the rate of the reaction, and therefore shows that the equation only comprises of iron 3 and thiocyanate crystals. Adding the sodium phosphate allowed the solution to turn from red to clear. This means that the concentration of the product iron thiocyanate decreased, which meant that the reactants decreased due to the addition of H2PO4-. Therefore, the reverse reaction increased to add more reactants. The color of the solution changed back to red when Fe3+ was added in step 9. The color change indicated that thiocyanate was present, which reacted with the Fe3+ added. In step 10, when SEN- ions were added, the solution turned red. This means Fe3+ ions were present in the equilibrated mixture reacting with the added thiocyanate to form the dark red iron thiocyanate.
6. When the solution was heated, the color changed from yellow to pale yellow, meaning that yellow product decreased. When the solution was cooled, it turned to dark yellow, meaning that the yellow product increased. This shows that the reaction can go either way. And when the solution was cooled, it was an exothermic reaction for number 7, and when it was heated, it was an endothermic reaction, and we have our equation right here.
Based on the rules of Henry's law, if the amount of carbon dioxide dissolved in the seltzer water is proportional to the pressure of the carbon dioxide gas above, A decrease in pressure will lead to the amount of carbon dioxide to become smaller, while an increase in pressure will cause the amount of carbon dioxide to increase in the seltzer water.
To start off, obtain approximately 10 milliliters of fresh seltzer water in a 50 milliliter beaker. Add about 20 drops of 0.04% bromocresol green indicator. Swirl to mix the solution. Drop about 10 milliliters of the seltzer/indicator solution into a 30 milliliter syringe. Seal the syringe by pushing a tip cap firmly onto its open end. Record the initial pH of the seltzer/indicator solution and volume of the gas along with the liquid.
Next, pull on the plunger to expand the volume of gas, shaking it at the same time. The solution will become bluer as it becomes less acidic. When the color stops changing, stop shaking and record the new volume of gas. Then, determine the pH of the solution by comparing it to the chart and record. This time, push on the plunger to compress the solution while shaking it. The solution will become greener as it becomes more acidic. When the color stops changing, stop shaking and record the new volume of gas. Record the pH of the seltzer solution as well.
This is the color chart for the bromocresol green used in the experiment. It is used to correlate the color of the indicator with the pH. On the chart, yellow has the lowest pH, green has a neutral pH, while blue has the highest pH level.
The pH correlates to the amount of hydrogen ions in the solution, as shown in the chart.
Results. In the experiment, we conducted 3 trials, which allowed us to see the common patterns that occurred for the steps. All of the trials had an initial pH of 4.3, being the color green. The first times we withdrew the plunger, expanding the overall volume, led the pH to increase and the color of the seltzer solution to change to a blue-green. When we compressed the plunger, the volume of the liquid plus the gas was lessened, resulting in the pH of the solution to decrease and the color of the seltzer solution to become a green.
Our experiment demonstrates the effect pressure has on a system state, following Châtelier's principle. Each time we had pulled on the syringe, we forced the carbon dioxide to be removed from the seltzer solution as a result of the decrease in pressure. The decrease in pressure caused the equilibrium to shift towards the side with the most moles of gas. In this case, the reverse reaction is favored. As a result of the loss of hydrogen ions, the pH of the overall solution increased, and the seltzer water became bluer and darker. For the times the plunger was compressed, the increase in pressure led to favoring of the side with less moles of gas, forward reaction. The forward reaction rate rose due to the compression, temporarily speeding up the reaction in that direction until equilibrium is once again achieved. Consequently, the pH of the seltzer solution decreased and returned to its initial green color. Thank you for listening to our presentation.